Hi folks, welcome to the first part of the calculus review for the Math SL exams. There are just a few disclaimers up here on the screen. So this isn't produced by IB, nor is it endorsed by IB. It's just a little review that I made up for my students in PEI Canada. It's a calculus refresher. If you're using this to teach yourself the material for the first time, you'll probably find that it's not that helpful. To make the most of the presentation, probably going to work out best for you to print off the notes and do the work in advance and use the presentation to check. As always, if there's a different way that you've been taught to do some of this work that makes sense to you, by all means, please do that. I'm not trying to be prescriptive about your approach. Alright, so first principles to start off. The derivative function is limit as h goes to 0 of f at x plus h minus f at x all over h. This is really just from slope formula. M equals y2 minus y1 all over x2 minus x1. It's just we're picking points that are infinitely close together. So often called first principles. You might be asked to find the derivative function of a polynomial using first principles, but probably nothing more difficult than that on the exam. The derivative of some function f at x is written f prime at x and gives the slope of the tangent at any point. So if I have a curve like this and I want the tangent, say, right here, that's just how steep the curve is at that point. The slope corresponds to the instantaneous rate of change of the curve. Wherever f prime at x is 0, or the slope is 0, we might have a maximum or a minimum. So if you think about this little sketch that I drew up here in blue, where's it going to have a horizontal tangent? Well, probably right here. It looks like it's going across, and that corresponds to a maximum on the curve. Here we're going to have a horizontal tangent as well. It's a local minimum on the curve. And you could also have points of inflection where you have horizontal tangents. Really what we're saying here is that interesting things happen on the curve whenever you have f prime equal to 0, or wherever you have a horizontal tangent. Sine tables or the second derivative test help us determine which is occurring, whether it's a max, min, or point of inflection. So if at some point A you find that the derivative is negative, is less than 0. That means f is decreasing at that point. The original curve must have been decreasing. If instead you find that f at some given x value is positive, that's telling you at that point f is increasing. And if you have a change from either decreasing to increasing, meaning that your derivatives go from negative to positive, or vice versa, you must have had a max or a min. We'll put that to use in the second presentation that's going to be around this topic of calculus that's going to have more applications. This presentation is mostly going to be just applying our rules. Second derivative of some function is written f double prime and tells us about the concavity of the curve at any point. If f double prime is negative at some point, the original curve is concave down. And I like to think of that as a spoon facing downwards. If f double prime is positive at some point, the original curve is concave up. An inflection point indicates a change in concavity. Okay, so at an inflection point, you get a second derivative of 0, and you get f double prime changing signs around this point. So if I had, say, this, the curve changes from spoon facing down to spoon facing up, right here where I drew in the red dot. It used to be facing down, now it's facing up. That means that red dot is a point of inflection, and we would have changed from having a second derivative that's negative over here to a positive one over here. If instead I had had a curve that did, say, this, again, I'd have a point of inflection where it changes concavity. It would have started off, in this case, positive, and then turned negative. But that red dot would be, again, a point of inflection. You can also have points of inflection that give you, instead of, in these cases, non-horizontal tangents, you could have ones, like in the case of a cubic graph, where you've got a change in concavity, right around here, goes from pointing down to pointing up. Okay, so second derivative goes from positive to from negative to positive, and you get this point of inflection right here, where you have a horizontal tangent. Second derivative test. So if at some point you find that f prime at a is 0, that means you've got a horizontal tangent. And the curve is concave down. Okay, so let's see if we can draw this. Horizontal tangent and the curve is concave down. I must have found a maximum. So that's one way to test for whether you have a max or min. If you've got a horizontal tangent and you find concave down, which means second derivative is negative, then that must be a maximum. Second case here, if f prime at a is 0, again, that means that we must have a horizontal tangent. But we have f double prime that's positive, meaning that it's concave up. There's only one way I can draw that, so that I have a horizontal tangent at this point a, and be concave up. And that's to have a minimum right here. You can also use sign tables on the first derivative to determine whether it's a max or min, but the IB often likes to ask a question somewhere along the line about second derivative test. Okay. And again, we'll put that to use in the second presentation around calculus. Okay, I didn't put this slide into the handout, but it's just a set of rules for differentiation from the Hayes-Harris textbook. So feel free to pause, go through it here. But it's got all of our basic rules for differentiation. And then the rules for integration at the bottom. Now, you can compare that to what you have in your formula booklet. I would think for the most part during the exam, you wouldn't want to be referring a whole lot to your formula booklet for derivatives and integrals. You'd want to know these pretty well. But of course, if you forget, they're here. They've got first principles up there. They've got derivative of trig functions of e to the x, ln x, x to the n. They've got the chain rule, product rule, quotient rule, and your standard integrals as well as formulae for area under a curve and volumes of revolution. We'll do a volume of revolution in this presentation. Okay, so that's what you get in your formula booklet on the exam. All right, let's do just a bunch of derivatives here to get into the swing of things. So if I have 4x to the 3 over 2 minus 3 ln x minus e to the power of 4x plus 1, this has got a whole bunch of parts to it. And each one of them we need to differentiate. So we'd have, okay, this 4. Now that x to the 3 over 2 is going to go down by 1, its power, and the 3 over 2 comes out front. Minus 3 times, because there was a coefficient of 3 here, the derivative of ln x. Okay, derivative of ln x is 1 over x. And this is the one of the ones you can check with your formula booklet. Minus e to the 4x plus 1. Well, I'm still going to have e to the 4x plus 1, and I'm also going to have to multiply it, because of the chain rule, by the derivative of 4x plus 1, which we know is just 4. Plus cos of x. Okay, derivative of cos x is negative sine x. Plus 2, derivative of 2, or of a constant, is just 0. Okay, let's make this look a little bit prettier. Put together any coefficients we have. 4 times 3 over 2 is just 6. X to the half, you could write it as root x. Minus 3 over x. Minus, this would look nicer as 4 e to the 4x plus 1 minus sine x. So that's just getting us started on some function that has a bunch of different parts to it. Okay, we've got most of our basic rules dealt with in there. B, x sine x. All right, if you have two x's and there's no plus between them, you should be very careful. It's always very sad when I see people missing the product rule. Here you've got really two functions that are being multiplied together. If you thought of it as composites, an x times a sine x. product rule. Prod rule. So, product rule is essentially first times the, or rather, derivative of the first times the second plus first times derivative of the second. So for us, that's going to be derivative of x, which is just 1, times the second part, sine x, plus first part, which is x, times the derivative of sine x, which would be cos x. This should be f prime. So we get sine x plus x cos x. Just watch out for the product rule as you go along. The next one, you have 3x times root x. So you might be thinking here, this would be a good candidate for the product rule. You absolutely could do this with the product rule if you wanted to, but there's really not any point. Sometimes the best thing to look for is some way to simplify the expression before you go ahead and differentiate. So this really means 3x times x to the half. Well, we know from our exponent rules that if I've got the same base of x, I can just add my exponents, which were 1 and 1.5. So this would be 3x to the 3 over 2. If I differentiate that, then I'm going to have 3 times the power, 3 over 2, times x to the power of 1 less than 3 over 2, which should just be a half. Which should give us 9 over 2 root x, or x to the half. Now, again, you could have done that with product rule, but if you can have some intuition for looking for ways to simplify first, it may make your life a little bit easier. F of x is sine squared of 3x. Okay, remember what sine squared means. It means sine of 3x all squared. So that squared is really on the outside. This is going to call for chain rule, which means derivative of the outer. So I'm going to take this 2 down front. We get 2 sine of 3x. The power of that is going to go down by 1 now, so it's just to the power of 1. I don't even really need to write it. Now times the derivative of the inner. So the derivative of sine 3x, well, derivative of sine is going to be cosine. Of 3x. And we're going to need chain rule again, because it wasn't just x, it was 3x. So times the derivative of 3x, which is just 3. So 6 sine 3x cos 3x. Okay, and if you're feeling really ambitious, you could also write this as 3 sine of 6x, using your double angle formulas. You really wouldn't have to go that far, but it's kind of a neat property on that one. This would be fine, though. All right, next one. Harder to miss the quotient rule. So here we can use quotient rule because we've got obviously a top and a bottom part. Since you've got a monomial on top, though, it might be easier to simplify this piece by piece. So 5x squared over x. Notice I'm not differentiating yet. I didn't write f prime. 5x squared over x is just 5x. Minus 3x over x. Well, that's just 3. Plus 2 over x. Now you might be saying, well, you lost some of your restrictions. I still have all my restrictions in there because this function still only exists for x not equal to 0. All right, now let's differentiate. Derivative of 5x is 5. Derivative of negative 3 is 0. And this expression here really was 2 times x to the negative 1. So we can bring that power of negative 1 down. So it'll be 2 times negative 1, or just negative 2. And the power of x to the negative 1 goes down by 1. You get x to the negative 2. So 5 minus 2 over x squared would be our derivative. You could also have done this one with quotient rule. Probably would have taken a little bit longer, though. All right, the next one. So you might say, oh, well, I want to do the same thing. I want to divide the first part by x and the second part by 3. So the 4x squared divided by x, the negative 1 divided by 3. Can't do that. We'd have to divide by the whole bottom of x plus 3. So it really doesn't make any sense here for us to try and reduce this before differentiating. Instead, we'll just use quotient rule. Okay, which tells us take the derivative of the top, the 4x squared minus 1, that's just 8x, times the bottom, x minus 3, minus top times derivative of the bottom. Okay, derivative of x plus 3 here would just be 1, all over bottom squared. Let's try and collect some like terms here. We'll just expand out. That'll give us 8x squared plus 24x minus 4x squared plus 1. Or rather, plus... plus 1. Okay, little smartboard issue there. Okay, coming back, all over x plus 3 all squared. Okay, put together our like terms, 4x squared plus 24x plus 1 all over x plus 3 all squared. There's nothing we can do to factor the top to try and simplify this, so that's as far as we could take it. Okay, next one. Looks like we've got a composite here where we've got ln of, and then we're going to need quotient rule. One of the nice things that happens when you're taking the log of some function and then you want to differentiate it, you can use your log laws here. So if I know that if I have ln of a over b, I can rewrite that as ln a minus ln b. Well, that means I can rewrite this function as ln of 2x minus 1 minus ln of 3x squared plus 1. Becomes a lot easier to differentiate this way. So ln of 2x plus 1 is just going to be 2x minus 1. 2x minus 1 on the bottom, and its derivative, which is just 2 on top, minus 3x squared plus 1 here on the bottom, and its derivative on top, which would be 6x. And we can just leave it that way. It's going to be a bit miserable to use quotient rule along with chain rule on that one. All right, this next one. When you see something like this to the power of 5, you might be tempted to expand. That's going to be a waste of your time. This is really just a case where chain rule should be applied. Okay, so power of 5 comes down front. Power of the whole thing goes down by 1, so instead of power of 5, now it's power of 4. Now derivative of the inside, which would be 6x squared minus 3. Poof, we're done. Okay, a lot faster than multiplying the whole thing out. All right, indefinite integrals. So there are rules for indefinite integrals given in your formula booklet. Okay, right here. Standard integrals are right here. Or in that little handout that I gave you. Okay, so taking a look here at 3x to the 5th. If we know our rules of differentiation really well, that will get us through most of our integration anyways. But here we had 3x to the fifth. Okay, I know if I integrate that, x to the power of 5 is going to have to go up to an x to the power of 6. And what I'm going to need out front is a 1 over 6 to counteract the fact that that 6 would come down when we differentiate. Okay. Integral of cos is sine. So we'd have minus sine x plus the integral of 3 over x is the ln of, ideally, absolute value of x, or just ln x. And we need our 3 out front because we had a 3 here. Okay, the last thing you need to make sure you remember when you're finding indefinite integrals is plus c. There could be any constant tacked on to the end. So simplified will give us 1/2 x to the 6 minus sine x, 3 ln of absolute value of x, plus c. You can always check your indefinite integrals by differentiating. So if I differentiated this, I get 1/2 times 6 x to the fifth minus derivative of sine x is cos x plus 3 times derivative of ln x is 1 over x, and the derivative of a constant is just 0. If I simplify that, I get 3x to the fifth minus cos x plus 3 over x. Oh my gosh, which is what we started with. Okay, so when you take the integral and differentiate it, it should give you the exact same thing as you're asked to integrate. All right, the next one, e to the 3x minus 1. When we integrate, it's still going to be e to the 3x minus 1. And we're going to need a plus c on the end. The problem is, if I tried to differentiate this, I'd end up with a 3 out front because of the chain rule. So I need a 1/3 to counteract that. C. Okay, integrate 5. Well, what would differentiate to give you 5? 5x, and we need a plus c. Again, you can check. If I differentiate 5x, I just get 5 plus derivative of c, which is 0. This is working out for us. Okay, part D is using substitution, which is a little bit beyond the curriculum as it stands right now, but that's going to change soon. Okay. Looks bad to start with, because we've got an x and a cos x squared. If this were differentiation, we'd be thinking, okay, I probably want to use product rule. But we don't have anything like that that we know, at least so far, for integration. So substitution is not in the current syllabus. But I thought I'd throw it in here just for fun. Okay? You can rewrite this in terms of some other variable u and say that let u equal this x squared over here, which means that du by dx would be 2x, just the derivative of that u. So if I differentiate x squared, I get 2x. And we have, in that case, since we have this x over here, we don't have a full du by dx, we just have a half of one. So now I can just rewrite this whole expression. I've got the integral of half of a du times cos of that x squared we just called u. Okay, that looks horrible written that way. Let's just switch the order. Half cos u du. This is easy for us to integrate. So the integral of cosine is sine. I'd have this half out front. Sine u plus c. So I integrate with respect to u here instead of with respect to x. And now I can just sub back in, since I know that u is just x squared. Half sine of x squared plus c. Okay. Now, you can double check that using differentiation. But again, it's probably not going to show up in your exam because it's not in the current syllabus. Find the following definite integrals. Okay, so definite integrals your GDC does. So let's start off with just looking at this first one with your GDC. If I saw this on paper 2, here's what I'd do. Y equals 3x squared minus 1. Boom. Graph it. Oh, I'm not surprised. That's a parabola. Okay, go second calc. Down here, there's my integration. Find the integral from -2 to 3. And it tells me the answer is 30. Okay? So that's all I'd have to do on a paper 2. On paper 1, though, you need to be, well, obviously more analytical about it. So you need to integrate 3x squared minus 1. So an x squared is going to become an x to the third. And that would give me my 3 in front when I differentiate. So that's just x to the power of 3 and minus x. And that's from -2 to 3. Now, people use different notation here when we're talking about these boundaries. Any acceptable notation is fine. So some people use a vertical line like that. It's all good. Now what I've got to do is plug in the 3 to this expression, the x cubed minus x. Okay, so that's going to give me 3 cubed minus 3. And I'm going to subtract off what I'd have when I substitute in -2 for the whole expression, which will be -2 cubed minus -2. A lot of brackets happening here. So this would be 27 minus 3. My first one's here, and this one would be -8 plus 2, or 24 plus 6. Oh my gosh, we get the same answer. Now, even though this has applications in area, for the definite integrals, you're not going to write unit squared here because it's not explicitly a question about area. All right, let's try the next one. Again, if this were paper 2, you would definitely just plug this into your calculator. Don't waste your time. However, if it's paper 1, we need to integrate or anti-differentiate. That'll give us e to the x. All right, now the integral of sine is negative cosine. I'm going to need negative cosine of 2x. I'm going to need a half out front from 0 to pi. Okay, again, you can double check that with differentiation to make sure it's the right integral. Okay, let's put in pi. We get e to the pi minus a half cos of 2 times pi minus e to the 0 minus a half cos of 2 times 0, which is just 0. Okay, that gives us e to the pi minus half cos of 2 pi. The cos of 2 pi is 1, okay, because it's 360 degrees. It's a full revolution. So we'd have negative a half times 1, or just negative a half, minus e to the 0. Don't make the silly mistake of calling this 0. It's 1. Minus a half times cosine of 0, which again is just 1. So negative a half. Okay, so we get e to the pi minus a half minus another half over here. I just want to work that out. So e to the pi minus 1. There's our exact version of that definite integral. Volumes of revolution. For some function y equals f at x, the volume created by rotating the function about the x-axis over some interval ab is given by. This is how it appears in the Hayes-Harris book. This is how it appears in your formula booklet. They mean the same thing. You've got to square the function before integrating, and you also multiply it by pi. Find the volume of the solid form by rotating this curve about the x-axis. and it should touch the x-axis right here at 3. So the whole thing exists from negative 3 to positive 3. I kind of like this version over here, but either one's fine. So I know I'm talking about pi times the integral from negative 3 to positive 3 of the whole function squared. So I have to take 2 root 9 minus x squared and square it. And it's with respect to x. Okay, before I integrate, I want to square that function. So 2 squared is 4. The square root of 9 minus x squared, all squared, is just 9 minus x squared. Now I could take that 4 out front. Maybe that's the easiest thing for us to do here. Or I could multiply it in and call it 36 minus 4x squared. Doesn't matter. So I can pull it out before integrating. Gives me 4 pi. Again, if you've got a subtly different way of doing this that gets you to the right answer, fantastic. Please do that. So I get 4 pi times. Okay, finally we get to integrate. The integral of 9 is 9x minus, this one's going to be an x to the power of 3. I need a 1/3 in front. Poof, from 3 to negative 3. All right, let's get some big brackets here. This is going to be whatever I get when I sub in 3 to the whole function. Okay, so 9 times 3. Maybe I'll do that in green to keep it clear which part is which. 9 times 3 is 27, minus 1/3 times 3 cubed, so that's 1/3 times 27. That would give us 9. Now I'm going to see what happens when I plug in negative 3 for the whole function. So I'll have minus 9 times negative 3 is negative 27. Negative 1/3 times negative 27 here is going to give us positive 9. All right. Let's do what's inside the brackets. So this would really be 27 minus 9 is 18. Minus negative 27 plus 9 is negative 18. Okay, that's 4 pi times 36. And 4 times 36 is 144. So 144 pi. What's the volume? Well, volume should have some sort of unit. So we're talking about units here, and they'd be cubic units. Folks, there's going to be a second calculus review presentation, so feel free to tune in for that. Good luck on your Math SL exams.